So what we were doing yesterday was we were showing how to use the integrating factor to solve a first order linear differential equation. And this was the equation. And what you do is you take your differential equation, put it in standard form, and once it's in standard form, you can identify this term in front of the y expression as p of x. The integrating factor is called u of x, and all you have to do is take e to the integral of p of x dx. So you take your p of x, put it in here, integrate. So you factor out the 2, you integrate 1 over x dx, which is the natural log of the absolute value of x. You bring the 2 inside the natural log, so it becomes the exponent. And then you can, the e to the natural log of x squared is just x squared. So that's my integrating factor. And so what when we multiply the first order linear differential equation by the integrating factor, you do that. And what you notice is that this term's derivative is, well, let's go down here. Once we simplify it, the derivative of this term is that term. And the derivative of this term is that term. So you can combine those two together into the original function here, not the derivative, but the original function, times the original function here, not the derivative, and you put the prime on the outside. And if you use the product rule, you could go from here to there. Okay, so that's where we were, I believe. I don't think we had integrated anything yet. Oh yeah, okay, we had integrated. Okay, so we got into this point. So actually we did the whole thing. So it's just kind of, I'd forgotten that we did the whole thing. So we integrate, and the integral of this, the prime of something integral is just the term that's in the parentheses. And then the right-hand side, you just use your normal rules. Oh, yeah, we hadn't finished because you do want to explicitly solve for y. In these cases, it's not that hard. So we're going to divide both sides by x squared. Or multiply by 1 over x squared. Oh, that wrong button. Gotta lower myself here. Either got to raise my table or lower me. Too far up here. Okay. Woo! It's like riding a right. Feel like I'm riding a horse or something. Okay. So anyway, what you do is you get y is equal to divide everything by x squared. Ride 'em, cowboy. The one interesting thing that we haven't seen before is that the constant gets divided by x squared. So in all of our other solutions up to this point, we end up with just c by itself. But when you use the integrating factor, you always end up with c divided by the integrating factor. Okay, so now we'll just simplify things. So you get 3/4 x squared plus 2/3 x plus c divided by x squared. So that's the solution. That's called the general solution. And I can't remember whether we gave some initial conditions on this problem or not. If not, I'm going to make something up here. So let's say at x equal x equal 1, y equals 6. And the reason I chose x equals 1 is because if I let x equal 0, you'd be dividing by 0, which would not be good. So you set the left-hand side equal to 6. Substitute 1 in for x. And that should be squared, not cubed. So what do we get? 6 plus 3/4 minus 2/3 plus C. So C is 6 minus 3/4 plus 2/3. And we'll change that to twelfths. So that's 72/12 minus 9/12 plus 8/12, which is 71/12. So then you can plug that back in so that you get your particular solution. There you did. Okay. So we're going to circle back around here and do some stuff in class today, but I wanted to finish that off. So the first thing we're going to do is we're going to go back to homogeneous equations, and remember what that was is they're equations that are not separable. But by making the appropriate substitution, we can do the algebra and make it separable, and then possibly integrate both sides. Yes?
I think the 2/3 there is still supposed to be adding. You times it by 1 and then change the sign.
What did I do now?
When you plugged in...
Oh, I made it negative. How did I do that? I don't know. Thank you for pointing that out. Okay, yeah. So yeah, I made a mistake there. It should be that third line from the bottom should be plus 2/3, so we'll fix that. Sorry. So it's going to be plus 8 or minus 8/12. Okay, here we go. So that's wrong. That's plus. So that's minus. That's minus. So 72 minus 17 is 55, right? Is that right? 62 minus 7 is 55. Okay. So let me write this problem down on the board that we're going to work on. So it says, transform the following homogeneous equation into one which is separable. And really, it's just algebra, but so we have x times x plus y times y prime is equal to y squared. And the reason it's not separable is this term. We're adding x and y, and so there's nothing we can do about that. The two substitutions you make. Oh, is it homogeneous? Yes, because really the key part is here you just have x plus y. If you had x plus y squared or x squared plus y, then it wouldn't work out. But because they're both raised to the first power, and so you add those together, so that's the only thing that would trip you up. So the two substitutions are that y is equal to new x, and that dy is equal to new dx plus x d new. And that's just using the product rule from a differential standpoint. So then what you're going to do is you're going to plug these in. So, well, no, we got one more thing to do. I forgot. So you got to rewrite your original differential equation by replacing y prime with dy dx. and then you multiply both sides by dx. So you get dy is equal there, and you get y squared dx. Okay, so at that point, you're going to make the substitutions up there. So for y, you're going to put in new x, and for dy, you're going to put in new dx plus xd new. Okay, and I'm going to let you work out the rest of it. I'm going to tell you what to do if you don't remember from your notes. So let's put this on. So I'm going to write the steps. First one, substitute. Second step, multiply out. Meaning eliminate parentheses. So we don't want any parentheses. Then you're going to simplify. And you can simplify by combining like terms. And dividing out common terms. And once you simplify, then you can separate the variables. And then, then we're going to integrate. And then substitute. You'll say that y equals, actually, yeah, so you're functionally in terms of new, so you have to, new is equal to y over x. So you'll substitute for new, since your separable equation will be in terms of x new. So then once you integrate, then you substitute back in for new, so it becomes in terms of y and x. So that's the process. So I think you'll end up with 4 terms on the left-hand side, because you're going to have, you've got x plus y in parentheses, and then y prime has 2 terms to it, or dy has 2 terms to it. So you'll use FOIL to expand all that out. So that's, if you didn't get that, look at it. And the way you look at it is this x here is this x. Okay, that's why I did it this way, just to keep it straight. So I'm going to show you the first term. So you've got that term. When you do first, you're going to have this x, you'll have this nu, and that dx. Okay, so that's kind of the way it works if you work through it. So like I said, if you don't understand that, let me know and I'll look at your paper. And the next step I would do is I would combine the x's, okay? Or I might divide by, looks like I can divide by something, like x squared maybe. So I'd probably simplify it down so I don't have x times x, I'd have x squared. I would put x times x squared into x cubed. And then you look, once you do that, you can look to see if there are any terms that are the same, which I think there should be. But I don't know until I simplify it. You just got to be very careful. Yeah, so I do see two terms that are the same, or they're of the same type. So hopefully you'll see that. So look at it. So you can see here that these two terms are the same. So if I subtract this from both sides, it'll eliminate those two terms. And then you see I've got x squared, x cubed, so I divide every term by x squared, gets me down to that point. So that's the simplifying. So that's done. That's done. Now, to separate the variables, all you have to do is put the terms that involve dv on one side and the ones that involve dx on the other side. And you'll notice I've still got a common x term here. It's not over here, that's why I couldn't eliminate it completely. But if I factor out the x, I'll have d nu plus nu d nu is equal to negative nu dx. And then I could factor out a d nu on the other side. So you'd have x times 1 plus nu times d nu equals negative nu dx. And then I separate the variables. So you'll end up with, what I will end up with 1 plus nu over nu all times d nu is equal to negative dx over x. So that's a separated variable problem. Ta-da! Okay. That's as much as you're going to have to know to do on the test is to get to that point, which is basically substitution, algebra simplification, factoring stuff out. Now at this point you can integrate it. So I'm going to work through this just to show you what you would do. So let me add a page here. So first thing I do is I make this two terms. So I'd have 1 over nu plus 1 times d nu is equal to negative dx over x. And then I integrate both sides. So the integral of 1 over nu d nu is going to be the natural log of the absolute value of nu. The integral of 1 d nu is going to be just nu. The integral of this is negative the natural log of the absolute value of x. So that's the integration part. And then you substitute back in nu is equal to y over x. So you get the natural log of the absolute value of y over x plus y over x is equal to negative the natural log of x. And I should have added an arbitrary constant, at least one, so let's put that in there. There we go. It's kind of messy, right? It's a solution. It's probably not something we could solve explicitly for. It's an implicit equation, but it is a solution, and it does work. Nobody said life is simple. Okay, so let's look at the one on the back. Now that we've gone through that one, you'll see. So it says, transform the following homogeneous equation into one that is separable. So go ahead and I'm going to leave this up to you. I'm going to give you more time to get ahead because you've just done the last one. And all we're going to do is get to the point where we're going to make it separable. We're not going to integrate it. And I got to run to my office. My headphones just started dinging. So. Okay, so I'm actually recording this outside of class because I somehow, I think it was when I had my headphones run out of power. Anyway, I'm just going to watch the video and comment. So this is another example of solving a homogeneous equation. So the first thing you do is you replace y prime with dy dx. And then you're going to multiply all the terms by dx to get rid of the numerator in that term on the left-hand side. So we get that. And then we can make the two substitutions, which y is equal to nu x and dy is equal to nu dx plus x d nu. Remember, that is just using the chain rule on the first expression. Okay, so now for y you plug in new x, dy you put in new x dx plus xd new. So that's the left hand side. The right hand side we're going to substitute new x, or x new x, quantity squared, whole thing, times dx. Notice the parenthesis there to make sure we multiply the whole thing by dx. So now we're going to multiply everything out, get rid of the parentheses. So first we have a 2, and you've got three terms, 2x times new dx. And so you'll see that there are two x's. So you get x squared and new squared dx. Okay, the next one is we do the next part of the dy part. So multiply by x d new. So you get 2x cubed new d new. And the right hand side, we just have to multiply out new x squared. Then we look to see if there are any terms that are common. So you'll see that we have x squared new squared on the left hand side and x squared new squared on the right hand side dx. So we're going to subtract new squared x squared dx from both sides. It doesn't matter what order I show the two things in, so you'll see they're opposite. It's the same result. So we eliminate one of the terms. So we're down to 3 terms. Then we're going to move everything that involves dx to one side. Well, actually, no, we're going to divide by x squared first. So we've got that as a common term at each factor in each term. In the second term, we have x cubed. So x cubed divided by x squared is x. Okay, now you're going to move the first term, new squared dx, to the right hand side. So it becomes negative. Then we, on the right hand side, we're going to factor out dx. That leaves us with 1 minus new squared. And now we can separate the variables. So you have 2 new squared over 1 minus 2 new divided by 1 minus new squared times d new. On the right hand side you get dx divided by x. So that's the separated equation. And then we could integrate that if we wanted to. The right hand side would be the natural log of the absolute value of x, and the left hand side would be negative the natural log of the absolute value of 1 minus new squared. And you'd add an arbitrary constant onto one side. So I think I'm going through the procedure again. Replace y prime with dy dx, multiply both sides by dx, make the appropriate substitutions. Then, there's the appropriate substitutions. Multiply everything out so that you don't have any parentheses left. Just got to keep track of those terms. So there we go. We got the first 2 terms times the first term of the dy part, and the first 2 terms times the dx, the x d new part. And then on the right hand side we've got x squared plus new x squared, which is new squared x squared. And subtracted the common term, so we can eliminate that last term on the right hand side. So that's the first step in simplification, and we get that result. Then we look for a common term. Usually it's x squared, something like that. In this case it was x squared. So we divide everything by x squared. Then you move all the stuff involving dx to the right hand side, and factor out the dx. And sometimes you can factor out an x too. Depends on what, where you go with the whole thing. And so we divide by x, divide by 1 minus nu squared. And there you go. Okay, let's see what's coming up next. Okay, so then I'm going to integrate both sides. So the left-hand side, u would be 1 minus nu squared. So d nu, du would be negative 2 nu d. There we go. So u is 1 minus nu squared. Du is equal to negative 2 nu d nu. I have positive 2 nu d nu, so that's where the negative sign comes in in front of the natural log. And u is 1 minus nu squared, so when you integrate that you get natural log of absolute value of u. Here we're now substituting in y over x. So y is equal to nu x, or nu is y over x. So now we have a equation. It's not explicitly solved for y, but it is it's an implicit equation for relating x and y. So I think if you were actually wanting to solve this, you would you'd probably move the negative sign to the right hand side. Then you'd do e to the x of everything, and then you'd have to ultimately take the square root of y, which would give you a plus or minus solution. It would give you two branches. It wouldn't be a function. It would be a function of x. It would be an implicit function. Okay, let's see what we're doing next here. Okay, so the next thing is this logistic growth problem that was on the handout. So we have 200 buffalo in this environment at time t equals 0. That's called the initial condition. And then we're going to have the carrying capacity, which is obviously going to be more than 200. So we're going to let it be 2,000 buffalo. So that's the maximum that we're going to allow because of competition. And at 12 years, we're going to say that the population is 1,400. And I want to find both the equation and the value of the function at 20. So once we get the equation, we can use that to kind of predict out what the population is. So we need to find out what B is and what K is in the logistic growth expression. So the logistic growth function says that the population as a function of time is equal to the carrying capacity divided by 1 plus B times e to the minus kt. So we can use the initial condition to find B. So we have t equals 0, and okay, so then the next thing we're going to do is we're going to use the value of the function at 12 years to find k, and then once we have the equation, we can use the equation to find the value of the function at 20 years. That's the kind of process we're going to go through here. Okay, so now I'm going to proceed. So we have set the population at 200 when t equals 0. So you'll get e to the 0. E to the 0 is 1. So we have 2,000 divided by 1 plus b. And you can see that I could put the 1 plus b up on the left-hand side and move the 200 to the denominator. So 2,000 divided by 200 is 10, and then subtract 1 for both sides. You get b is 9. So that is going to be the constant b. Okay, so there's b equals 9. So let's add a page, and now we'll find out the constant k using the value of y at t equals 12. So we plug in our just calculated value for b, and you'll see the only unknown we have once we put 12 in there is k. Okay, so again we can exchange the denominator on the right hand side with the left hand side, so we'll get 2,000 over 1,400. And then we can subtract 1 from both sides to solve for 9e to the minus 12k. So 2,000 divided by 1,400 is 1.429. Subtracting 1, you get 0.429. Then you'll divide both sides by 9 to solve for the e part. And that quantity is 0.0476, and you take the natural log of both sides so that you can use the inverse properties of logarithms and exponents to get k where you want it to be. So you get negative 12k is equal to whatever the natural log of 0.0476 is. It's going to be negative something because natural log of anything less than between 0 and 1 is negative. Divide by negative 12 to solve for k. So once we have k, we have the equation. So we're going to solve for y of 20 starting in the next lecture. But that's it for right now.